Glassware calibration. Imagine you have a volumetric pipette and you want to pipette some volume with this pipette. If you check the pipette, it will say something like it would dispense 10 milliliters plus minus 0.02 milliliters. Now the 10 milliliters here, that is the indicated volume. It's indicated by the manufacturer to be 10 milliliters. And this 0.02 milliliters, that is typically the tolerance. Now, when you take this pipette and put it in a lab and you measure a volume with this pipette, you might not get 10 milliliters, but you get 10.016 milliliters plus minus 0.004 milliliters. Now, this here, the 10.016 milliliters, is called the actual quantity or the actual volume that you measured in a lab. Clearly, the indicated volume is not equal to the actual quantity or the actual volume in this case, which leads to the definition of calibration. Calibration is defined as the process of measuring actual quantity that corresponds to the indicated quantity. Let me write this down. Process of measuring actual quantity that corresponds to the indicated quantity. The question now is, what affects the actual volume? Well, if you think about it, temperature has a big effect on the motion of the water molecules. If you're at low temperature, the molecules will of course move slowly. So if I draw the water molecules here randomly, they will move slowly. And if you increase temperature, then of course these water molecules will have more velocity, indicated by a larger arrow. So temperature directly affects volume, and we can explain that using what we learned in kinetic molecular theory, right? Higher temperature, higher kinetic energy, more motion. Now let's take a look at some data. If I look at temperature in Celsius versus volume of 1 gram of H2O in milliliters, then I can see at 10 degrees I have 1.0014 milliliters. At 20 degrees, for example, I have 1.0029 milliliters. At 30 degrees, I have 1.0054 milliliters. So as the temperature increases, the volume of 1 gram of H2O increases. So larger volume at larger temperature. And that should make sense to us. Now a quick question, what effect does the temperature have on mass and weight? So the effect of temperature on mass or weight. And the answer is no effect. So it doesn't matter if it's 10 degrees or 30 degrees, it's still 1 gram. The mass doesn't change. Now think about it then. What happens to density, which is defined as mass over volume? As temperature increases, volume increases, and density decreases. And think about it. Buoyancy, density determines if something floats or sinks, right? Let's do a simple example where we obtain the volume of water from given mass measurements. Assume you have an empty weighing bottle, and the weighing bottle has a mass of 10.313 grams. After addition of water of 25 milliliters, so here's a volume of 25 milliliters, you measure this weighing bottle again with the water, and the mass was 35.255 grams. If the lab temperature was 28 degrees Celsius, find the volume of water delivered by the pipette. Now, what is given in this problem? In this problem, we are given the indicated volume, which is 25 milliliters, and we are given the masses. And my strategy now is to convert the masses into the actual volume. And in order to convert this to the actual volume, I need the factor from a table. Now, there's a table on the slide before, or there's a table in your pre-lab lecture, or there's a table found on Canvas that you can use. Either one works fine. Now, in order to calculate the actual volume, you basically just calculate the mass of the water, and that is easily done by subtraction. So 35.225 grams minus 10.313 grams gives me a mass of 24.912 grams. Now I simply convert these 24.9 grams into milliliters using the conversion factor. So at 28 degrees Celsius, the conversion factor is 1.0046 milliliters per gram. So 24.912 grams times 1.0046 milliliters per gram gives me a volume of 25.027 milliliters of actual volume in my pipette at 28 degrees Celsius. You might ask yourself, how close is the actual volume to the indicated volume? Well, the answer to this is easy. We can calculate the accuracy. Now, the accuracy, or better, the percent accuracy or percent error, is equal to the experimental value minus the true value divided by the true value times 100. Now, in our case, the true value is the indicated value, and the experimental value is the actual volume. And if we want to calculate this, we simply plug in our numbers. So we basically take 25.027 milliliters minus 25.00 milliliters, remember sig figs, divided by 25.00 milliliters times 100 gives me 0.108%, and 1 sig fig, so 0.1%. Notice that this is less than 3 to 5%, so very accurate. Notice that the effect on temperature has multiple forms. For one, if you're 20 degrees, which is where the manufacturer calibrates a pipette, and you add 25 milliliters to your pipette, if you then do the same experiment at 28, what happens is that water, the volume will expand, and also the glass will change its properties with temperature too. So you have two effects. The glass here will expand and the water will expand. If I only consider the water, then my theoretical value would have been 25.115 milliliters for 25 milliliters. But if you look at the slide before, we only had 25.027 milliliters, and that is because the glass also expanded. So when we do our calibration, we take into consideration the expansion of the glass and the expansion of the water, and we back calculate what the real value is based on mass, which is unchanged by temperature. Now that you have a good idea about what calibration is, let's talk about a little bit the procedure in this lab. You need to calibrate a 50 milliliter burette, a 5 milliliter pipette, and a 10 milliliter pipette. The two pipettes will be in your drawer, and the 50 milliliter burette will be stored in the lab, and you'll put a labeling tape with your name on it. That will be your burette that you will use for all experiments in Chem 210. let's take a little look at the procedure for the burette. So in the burette, we always have an initial volume. Remember, we read the bottom of the meniscus, and a final volume. Now, when you read the difference in volume, that is typically, you guessed it right, the indicated volume. Now, how do I figure out what the actual volume is? Well, what I'm going to do is I'm going to take an Erlenmeyer flask and I weigh the mass of the Erlenmeyer. And then what I'm going to do is I'm going to pipette some of the liquid into the Erlenmeyer flask, and I'm going to get the mass of Erlenmeyer plus water. And of course, the difference here in mass is the mass of the water. And if I take this mass of the water and multiply by my correction factor, which I get from the table, so you have to measure the temperature of today's experiment, that gives me the actual volume. And now I can do a comparison on my calibration. Now, what we're going to do is we're going to repeat these measurements and calculations for a total of 3 trials total. For each region, 0 to 10, 10 to 20, 20 to 30, 30 to 40, and 40 to 50 milliliters. So there's 5 regions, 3 trials total, and we have to wait 30 seconds in between every reading. So wait 30 seconds between each reading. Once you've done all your measurements for the burette, you have to do calculations, and we're going to do the calculations for each of the 5 regions. Of course, every time you have multiple trials, so here you have 3 trials, you need to do a Q-test to see if you've discarded one. You should calculate the actual volume and the correction term volume of the burette, which you get by subtracting the indicated volume from the actual volume. You should calculate the average burette volume correction. There's 3 trials for each region, unless you use the Q-test to disregard a trial, and then calculate the ASD/RSD confidence interval, which is the basic statistics, as well as the percent error. And of course, the percent error is based on the average and the 10 milliliters, because each region is 10 milliliters. Also in Excel, please make a graph of the correction factor on the y-axis versus burette region on the x-axis, so you get a nice little graph. Make sure to add this graph to your yellow pages, at least a sketch of it. The procedures for the pipette are very similar to the ones of the burette. We're going to have 5 ml and 10 ml pipettes that we use. And the indicated volume will of course be 5 milliliters or 10 milliliters. So how do we get the actual volume? Again, take an Erlenmeyer flask, weigh the mass of the Erlenmeyer flask. Then, for example, if you have a pipette, you pipette 5 milliliters into an Erlenmeyer flask. So here's my Erlenmeyer flask with water. The difference in mass is the mass of the water times the correction factor that gives me the actual volume. The 5 milliliters is the indicated volume. Remember, it's 5.00 milliliters, and then we can compare again. Now, how many trials? We do this 5 trials for each pipette. And so we have 5 trials for the 5 mil and 5 trials for the 10 mil pipette. Here the calculations are straightforward. Calculate the actual volumes, which is the mass times the factor from the table. So the mass of water times the factor from the table. Now that you have the 5 values, do a Q-test on those 5 values. Calculate the average, the RSD, ASD, confidence interval, and of course a percent error, where here the percent error compares the average volume with the indicated volume. And you divide by the indicated volume and multiply by 100 to get a percent. Let's have a look at example calculation for a volumetric pipette. So here we have a 10 milliliter volumetric pipette. We pipetted 10 times into an Erlenmeyer flask. We got the mass before and after and subtracted them. And then we multiplied the mass by the factor. So all this work is not shown. But here are the 5 volumes: 9.87, 10.04, 10.02, 10.04, and 10.03. If you look, that's 5 trials, so you have to do stats. First thing you want to do is a Q-test. So let's do a Q-test first. Now, what is a suspect? Well, either 10.04, but there's 2 of them, or 9.87, so I think this is the suspect. So I'm going to calculate Q experimental, which in this case is 9.87 minus 10.02, 10.02 being the nearest neighbor. Remember, nearest neighbor means the one closest in value, divided by the max minus min, the whole thing absolute value, and that gives me 0.88. Now, since n is equal to 5, I look up from the table at 90% confidence. What is the Q value? So Q critical is equal to 0.65. Now I have to compare 0.88 to 0.65. Now what is the condition? Q experimental is smaller than Q crit. Got to keep the value. If Q experimental is bigger than Q crit, reject. So in this case, since 0.88 is definitely bigger than 0.65, we're going to reject the value. So our new data would basically be just those 4 values here. And I would do all subsequent analysis and statistics just based on those 4 values, not 5. Let's do some basic stats. If I have these 4 values of volume, actual volume, basically what I do is I either put them in Excel or I put them in my graphing calculator, and you should know how to do the basic commands in Excel or a graphing calculator to get the average and the absolute standard deviation. And if I do this, then I get automatically my average, which is the sum of those 4 values divided by the number of values, which in this case is 10.0325. Remember, Excel or your graphing calculator don't have sig figs. So you're responsible to notice that all of these values are to 2 decimals, so this average will also sig figs be to 2 decimals. Now, the other value you get automatically is the ASD, or the S value, which is basically the square root of the variance divided by n minus 1. N is the number of trials, here 4, so we're dividing by 3, and the sum is the sum of all the individual values subtracted from the average, and of course squared because it's the variance. Now, in my graphing calculator on Excel, that number is 0.0 0.009574. There's a few other digits, but I'm saving them for right now. Now, you can you know that the sig fix of the standard deviation depend on the sig fix of your average. So you can record in your laboratory notebook the average volume, in this case that's the actual volume of the pipette, is 10.03 plus minus 0.0955, now needs to be rounded, 1 milliliters. So this would be my result that I would copy down in my laboratory yellow pages notebook. Now, how do I get the RSD, the relative standard deviation? Well, the relative standard deviation is basically the ASD divided by the average times 100. So in this case, that's 0.09574 divided by 10.0325 times 100. And that number is 0.095433. Now, how do I know what the sig fix are for this? Well, the sig fix for this, if you look, my absolute standard deviation has one sig fix, so this has one sig fix. So this would be 0.1%. And remember, RSD less than 1% is precise, which is good. Last but not least, we need the confidence interval. In the confidence interval, we need to look up two things. One, the t-value, and the t-value depends on two things. My confidence, my percentage, so in this case we use 95%, and my degrees of freedom. Degrees of freedom, which is n minus 1, which in this case is 3. So let's take a look at a table online and see what my t-value is. Now looking up the t-value, I get a value of 3.182446, etc. So this will be my t-value. Now how do I calculate the CI? Well, the confidence interval is plus minus t times s divided by square root of n, which in this case is 3.18 times, what is my standard deviation, 0.09574, divided by square root of, how many trials do we have? 4, and that gives me 0.151854. Now the only question is, how many sig fix? Well, confidence interval depends on the average, right? So since my average has 2 decimals, I need 2 decimals here, so my confidence interval is plus minus 0.15 milliliters. So let me recap. Take your 4 values of the actual volume from the pipette. Calculate the average and the standard deviation, which is the absolute standard deviation. This can be done with Excel or graphing calculator. Reported as follows: the average volume of the pipette is 10.03 plus minus 0.01 milliliters because of sig fix. That's important. Calculate the relative standard deviation, which is simply ASD divided by the average times 100. In this case, 0.1%, so it's very precise, less than 1%. Then calculate the confidence interval, which is plus minus t times s divided by square root of n, and t is a value that I need to look up. It depends on my probability, my confidence interval, and my degrees of freedom. The degrees of freedom are n minus 1, n was 4, 4 minus 1 is 3. Given that value, you just plug in all the numbers, or do it with Excel or your graphing calculator, and you get, using the right sig fix, a confidence interval of plus minus 0.15 milliliters. ASD, RSD, confidence interval were all measures of precision, how precise an experiment is. We also can do an assessment of accuracy, and in the assessment of accuracy, we're going to calculate the percent error or percent accuracy. They're synonymous. which is typically the experimental value minus the true value. So typically when we do accuracy, we need to know what the true value is, divided by the true value. Now, true value, we use the manufacturer's indicated value. And experimental value, we're going to use the actual volume that we determined in the experiment. So in this case, it's 10.0325. I'm going to put a 3 here for the sig figs, minus 10 milliliters. So 2 decimals, right? Divided by 10 milliliters times 100. All the milliliters will cancel out, so I didn't write them. So that gives me 0.325%. And how many sig figs? Well, if I subtract the top, then I will only have one sig fig. So my percent accuracy or percent error is 0.3%. This is less than 3 to 5%, so it's pretty accurate. Make sure you can do any of these calculations without taking a look at your Canvas page or your lab notebook pages. You should be very proficient calculating statistics and percent error from given data using your graphing calculator or Excel. I hope this helped, and good luck in the experiment.